This is lesson 4.3, patterns and nonlinear functions. Again, here in YouTube form, so you can go back and pause it, watch it, look up things whenever you need them. So we're going to talk about linear versus nonlinear. All right, so what it means to be linear is that it's going to create a line. So you can see these are all linear functions because they make lines. So the opposite of being linear is to be nonlinear, right? That would mean not a line. You can see that these three functions, they're different kinds of functions, but all of them do not make lines. So they are nonlinear. So linear is what we've been looking at, right? Linear functions make lines. Nonlinear functions make not lines. So they can make anything that is not a line as long as it is still a function. All right, so like here in this one, classifying functions as linear or nonlinear. So we have some points here. So we've got the point 1, 1. So we go right 1, up 1. And we have 2, 3. So right 2, up 3. We've got 3, 7. So right 3, up 7. We've got 4, 9. So right 4, up 9. And then 5, 12. So right 5, up 12. So then I can look at this graph. If I go to connect these, this is not going to make a line. So that's how I know that it is non-linear. I don't know what kind of function it is, but I know it's non-linear because the graph does not make a line. We can also do what we were doing before. From 1 to 3, you'd have to add 2. From 3 to 7, you add 4. So remember, if you're linear, you're always adding by a constant, adding by the same amount. Since you add 2 and then add 4, we know it's not linear. So that's another way to tell that it is nonlinear, right? Linear on your table, you go up by a constant amount. On your graph, you would create a line. Our next example, we've got the point 0, 10, 4, 6, 8, 10. Then we go to 2, 12. We go to 4, 14. We go to 6, 16. Then we go to 8, 18. So looking here at these beautiful red dots, I can see if I were to connect them, they would make a line. So that's how I know that this is linear, right? Points that when you connect them make a line means it's going to be linear. The other way we could check that, looking at the table, from 10 to 12, we add 2. From 12 to 14, we add 2. From 14 to 16, we add 2. From 16 to 18, we add 2. You're always adding the same amount. You're adding a constant there on your y's, so that's another way to know that it is linear. Now, yesterday we talked about writing an equation when it is linear, right? So since it's linear, we know it's y equals something x plus something, right? Y equals mx plus b. We know that the constant interval increase here is always our m in front of x. So this would be 2x plus our constant here. When x is 0, what is y? Well, when x is 0, y is 10. Right? So this equation here would be y equals 2x plus 10. That's what we were doing yesterday. Knowing it's linear, it's got this invisible exponent of 1 here. So what we're going to look at today is writing nonlinear functions, right? Nonlinear functions. So what is a rule for the function represented by the ordered pairs? 1, 1, 2, 4, 3, 9, 4, 16, and 5, 25. So I like to do this in table format, and you'll see why in a minute. I think it makes it a lot easier. So we've got our x values of, let's see, 1, 1. Then we've got 2, 4. We've got 3, 9. We've got 4, 16. And then we have 5, 25. All right, so if this is linear, then I know that I'm going to have a constant here. Well, to go from 1 to 4, I would add 3. To go from 4 to 9, I add 5. And remember, if you don't know what you're adding by, you can subtract in reverse. 9 plus what is 16? We'll go in reverse. 16 minus 9 is 7, so you'd add 7. 16 plus what is 25? Well, 25 minus 16 is 9. So you can see you did not get a constant. So that means this is non-linear. So what we're going to do is see if we get a constant if we try it again. Well, now on these numbers, to go from 3 to 5, I add 2. To go from 5 to 7, I add 2. To go from 7 to 9, I add 2. So this did not happen on the first. This is called an iteration. It did not happen on the first one, so it's not degree 1. It's not linear. It happened on the second one, so it is a degree 2. So this has something to do with y equals x to the power of 2. So it's going to be nonlinear because it has that exponent of 2. So since it happened on the second time, that's why the exponent is 2. Then we could plug it in with our numbers here and try it, right? If we plug in 1, well, if I do 1 squared is 1. So when I plug in 1, I get out 1. That works. If I try 2, 2 squared is 4. Well, that's perfect. 2 squared is 4. That works. 3 squared is 9. Works. 4 squared is 16. 5 squared is 25. So this is our function rule for these ordered pairs. Y equals x squared, right? 1 squared is 1. 2 squared is 4. 3 squared is 9, and so on. All right, let's look at 1, 1, 2, 8, 3, 27, 4, 64, 5, 125. So again, I'm going to put it in table format just to make it easier for my noggin to see the numbers and be able to look at where they're going to become constant. So this time we've got 1, 1, we've got 2, 8, we've got 3, 27, we've got 4, 64, and 5, 125. All right, so to see if it's linear, from 1 to 8, I would add 7. From 8 to 27, remember, if I don't know what that is, I can subtract and reverse. So I know 27 minus 8 is 19. 27 plus what is 64? Well, you can always subtract and reverse. 64 minus 27 is 37. 64 plus what is 125? Well, we can do 125 minus 64 is 61. So I can see we did not get a constant on the first iteration. So we'll go again to see if it's a x squared. Well, from 7 to 19, 19 minus 7, I would add 12. From 19 to 37, well, 37 minus 19 is 18. So I added 18. So I can already see that's not going to be a squared. To go from 37 to 61, I add 24. So it didn't happen on the second iteration. So this does not have anything to do with x to the power of 2. So I go again. This is as far as you'd have to go in Algebra 1, too, by the way. From 12 to 18, I would add 6. From 18 to 24, I would add 6. So there I go. There's my constant. It happened on the third iteration. So the exponent is going to be 3. This is going to be y equals x to the power of 3. And then we can try it, right? If we plug in 1, 1 to the power of 3 is 1. It works. 2 to the power of 3 is 8. 3 to the power of 3 is 27. 4 to the power of 3 is 64. 5 to the power of 3 is 125. So our function rule is y equals x cubed. I like these. They're kind of like a little game. All right, so let's keep those in mind and look at some that are just a little bit more difficult here. So we have 0, 0, 1, 4, 2, 16, 3, 36, and 4, 64. So we know that we're going 0, 0, 1, 4, 2, 16, 3, 36, and 4, 64. So I went backwards this time and put in the numbers first. Oh, that was a nice little straight line there, wasn't it? So now let's see. To go from 0 to 4, I add 4. From 4 to 16, I add 12, right? 16 minus 4 is 12. From 16 to 36, I add 20 because 36 minus 16 is 20. To go from 36 to 64, I add 28 because 64 minus 36 is 28. Didn't happen on the first try. Fiddlesticks. All right, so from 4 to 12, I would add 8. From 12 to 20, I add 8. And from 20 to 28, I add 8. So there's my constant. It happened on the second try, so that means it's something about y equals x squared. All right, but this one's a little bit more. So if I plug in 0, right? If I plug in 0, 0 squared is 0. So that works for the first one. But when I plug in 1, 1 squared is 1, and I need to be 4. What? When I plug in 2, 2 squared is 4, but I need to be 16, right? So I got 1, but I need to be 4. I got 4, but I need to be 16. 3 squared is 9, but I need to be 36. 4 squared is 16, but I need to be 64. So I have to look. I need to figure out what can I multiply these blue numbers by to get to the purple numbers, right? 1 times what is 4? 4 times what is 16? 9 times what is 36? The answer to that is always 4. So if we do 1 squared, we get 1. Then multiply it by 4. 1 times 4 is 4. 2 squared is 4. 4 times 4 is 16. 3 squared is 9. 9 times 4 is 36. So this time, we also had to multiply by 4. All right, let's try that concept again. That's a little difficult. So on the next one, we have 0, 0, 1, 3, 2, 24, 381, and 4, 192. Well, here we go. From 0 to 3, I add 3. From 3 to 24, I'd have to add 21. From 24 to 81, well, 81 minus 24 is 57. 81 to 92, well, 192 minus 81 is 111. So it's not a first iteration, so I'm going to go again. From 3 to 21, well, 21 minus 3 is 18. So we added 18. 57 minus 21 is 36. 111 minus 57 is 54. So the numbers are getting closer together, but they're still not there yet. So we go again in purple. So from 18 to 36 is 18. From 36 to 54, 54 minus 36 is 18. Yay, there it is. There's our constant. It happened on the 1, 2, 3, the third time. So it's something about y equals x to the power of 3, right? But not quite, because if I do 0 cubed is 0. However, I don't want 0. I want, oh wait, actually I do want 0. That one does work. When I plug in 1, 1 cubed is 1, right? But I don't want 1. I want 3. If I plug in 2, 2 cubed is 8, but I don't want 8, right? I need to be at 24. See? Next one, if I do 3 cubed is 27, but I don't want 27. You can see when I plug in 3, I get 81. So this is what x cubed gives me here, but I need to get over here. So I have to figure out what I have to multiply by. So I ask myself, I'm at 1, I need to be 3. 1 times what is 3? Well, that would be 3, right? I'm at 8, but I need to be 24. Well, 8 times 3 is 24. 27 times 3 is 81. So here we are multiplying by 3. Y equals 3x cubed. And that is lesson 4-3.